All right. So hello class. I know I missed you guys this morning. So I'm just going to do a quick talk about resistive index and high resistance versus low resistant waveforms. Because Kathy just wanted me to kind of review this a little bit with everyone because there was a little bit of confusion on one of her exams regarding high resistance and low resistant waveforms. And it's just an important topic, particularly when we're dealing with cerebral vascular circulation and really any artery in general, being able to differentiate between high resistance and low resistant waveforms and what that means in terms of disease processes when we have differences in what would typically be a normal arterial waveform for that particular organ or body segment that we're imaging. So just to kind of, go back over some of the things that we know already. The formula for resistive index, or RI, is our peak systolic velocity minus end diastolic velocity divided by the peak systolic velocity. So a couple of important things to remember when you're measuring resistive indice is to use measurements from the same waveform. Our waveform begins with systole and ends with diastole. So if you go over here on your arterial waveform, so your waveform is going to start with systole, so that's your systolic upstroke, and it's going to end with diastole. So diastole is the moment right before systole begins again, so that's end diastole. So this is your diastolic component. So I know when you guys were doing some of the carotids, you noticed that dicrotic notch in the waveform. That actually is the technical beginning of diastole. So when we're measuring resistive indice, we're gonna put our caliper on that peak systole, the top of that point, and we're gonna measure our end diastole at the exact end of the diastolic portion of that waveform. So right before you start your next waveform with systole. So if we use some of the numbers that I calculated here, so I just kind of made it easy for calculations. So our peak systolic velocity is 10. Our end diastolic velocity for this waveform is going to be 5. So if we put it into our formula, 10 minus 5 divided by 10 equals 5 over 10, which is 0.5 or 1/2. So in terms of high resistance versus low resistance, I typically like to think that a resistive indice over 0.7, you start getting into a high resistant waveform. Lower than 0.7 would be considered more of a low resistant waveform. But you also have to take into account which organ or vessel you're imaging, which artery you're imaging, because different organs will have different resistive indices, which are considered normal and abnormal. So if you look at another waveform, this one in the bottom corner, this would be a typical peripheral arterial waveform. So this would be considered a triphasic waveform because you have a component that actually reverses flow direction below the baseline. This would be a biphasic waveform. So with this waveform, we have a resistive indice, peak systolic is 10. Your end diastolic velocity, measured here, so would be 1. 10 minus 1 over 10, you have 9 over 10. So we get a resistive indice of 0.9, 0.9. So that would be a high resistant waveform. So another thing to also remember too is if you look at these waveforms here, all we see is a systolic component. So there is no diastolic component to those two waveforms. So when we have no diastolic velocities, or our end diastolic velocity is 0, changes in our peak systolic velocity, so this one's 5, this one's 50, will not have an effect on your resistive indice. So when there's no diastolic component, your resistive indice is going to be 1 because it's whatever your peak systolic velocity is. Say in this case 5, we're minusing 0. So it's still 5. 5 over 5 would be 1. Same case, 50 minus 0 is 50. Divided by 50 is 1. So anytime you don't see any diastolic velocities, your resistive indice is going to be 1. It will be Ri equals 1. Ri. Any questions about this? You know, you can shoot me an email. Be happy to answer. But that's it. Thank you.